lecture 15 of week 3. So, this will be the last lecture on torsion of thin wall structures. So, today we will solve certain examples on torsion of thin wall shaft, thin wall cross section shaft. Just to recap, we are dealing with closed cross section shaft with multiple cells. So, the example, the figure that I have drawn is a cross section of a shaft under pure torsion. As you can see that this is thin wall, the thickness is very small compared to the other dimension of the cross section, as well as this is closed and it has two cells. So, let me name the cells as 1 and 2. So, we have two cells and we need to find out if a torsion, so a torsional moment T is applied to the shaft, find the shear stresses in the shaft. So, this is what we need to evaluate. So, now let us draw the dimensions of the shaft. So, the dimensions are, so this has a radius of r. So, this is a semicircle with a diameter of 2r. So, this is 2r, this is r. So, though I have not drawn it perfectly, this portion, the portion 1 is a semicircle. Then we have this portion, the length of the horizontal length of this portion is 3r. And if we calculate this slanted portion or the side of the triangle is pi r. So, it is symmetric about the x axis. The cross section is symmetric about the x axis. Let us talk about the thicknesses. The thickness here is 3t. The thickness of this portion is 2t and the thickness of this portion is t. So, let me call this portion to be 2, this portion to be 1 and this vertical portion to be 3 and this area to be A1 and this area to be A2. Now, let us see how to analyze this cross section or this shaft using membrane analogy. So, let me first draw the deflected shape of the analogous membrane. So, this is the x axis, this is the z axis. So, if I draw the deflected shape of the membrane, the deflected shape would look something like this. So, we can even remove this z axis, so that we can we can visualize the thing better. So, this is the x axis, and this is the deflected shape of the membrane. So, this one is H2, this one let us call it as H3 and this one let us call it as H1. So, this is the deformed shape of the analogous membrane. I'll not say analogous membrane all the time. The membrane means the analogous membrane. So, this is the deformed shape of the analogous membrane. Now, let us, so I have drawn this picture arbitrarily. I haven't made any assumptions or certain consideration while drawing this picture. Now, from this picture, as we have done earlier, my tau 1 can be written as H1 by T1, which in turn is tau 1 into T1 is T. So, tau 1 into T is H1. Similarly, tau 2 is going to be H2 by T2, which again T2 is 2T. So, tau 2 into 2T is equal to H2. Similarly, tau 3 is H3 by T3, and which gives me tau 3 into 3T is equal to H3. Additionally, from this expression, we can also, from the geometry, we can say that H2 is H1 plus H3, which implies that tau 1, tau 2, T2 is equal to tau 1, T1 plus tau 3, T3, which again implies that Q2 is equal to Q1 plus Q3. So, from the geometry of the deformed membrane, we get this relation that Q2 is equal to Q1 plus Q3. That is one expression that we get. The other expression that we get is that from so if I replace the values of T1, T2 and T3, the other expression that we get is tau 2 T2, T2 is 2T, is equal to tau 1 T1, T1 is T, and tau 3 T3, which is 3T. So, from this we get that 2 tau 2 is equal to tau 1 plus 3 tau 3. So, this is another equation that we get, which we will be using later. So, let me call this as equation 1. So, these are the two expressions that we get from the expression for from the expression for the equations that we have. So, sorry, I just made a small mistake. So, this should be T and this should be 2T. So, this is 2T and this is T. So, if this is 2T and this is T, then I have to make small corrections here. And this is 2. So, I have this one. So, I have to make a small correction here. So, tau T is 2 tau 1 plus 3 tau 3. So, this is the equation that we have. Now, therefore, from the deformed shape of the analogous membrane, I get two equations. One equation relates the tau 1, tau 2 and tau 3, and another equation which relates the shear flow, that is Q2 is equal to Q1 plus Q3. Now, so let us look what does this expression denote. So, let me call this as equation A. So, let us see what equation A denotes. So, equation A denotes that if I assume that Q1 is like this, and if I say that Q2 is like this, then I have to say that Q3 is like this. So, which denotes that at this junction, if I call this junction as K, then at junction K, the input shear flow, which is Q1 plus Q3. So, let us look at the junction K. So, junction K, I have Q1 plus Q3 as the input, that is going to be the output shear flow. Which is Q2. And as we have discussed earlier, the total input shear flow at any junction is also equal to the output shear flow. So, therefore, from this example we see that we have got two information from this deformed shape of the membrane. So, one is a relation between tau 1, tau 2 and tau 3, and other is how the shear flows are arranged in the cross section. Now, let us move on to finding out the expression for the applied torque. So, we know that the applied torque or the torsional moment, that acts on the shaft, if that is T, so that is going to be twice into the deformed volume of the deformed membrane. So, for this case it can be written as A1 H1 plus A2 H2, where A1 is and A2 are the area enclosed by cell 1 and cell 2. So, if I substitute the value for A1 and A2, I will get this as A1 is going to be pi r square by 2 into H1 is going to be tau 1 into 2t, and A2 on the other hand is the area of the triangle. So, which is going to be half into base, that is 2r, into height, that is 3r. So, this is the area A2, and H2 is going to be tau 2 into t. So, this is what we have. So, if we simplify this, we have this as 2 pi r square t into tau 1 plus 6 r square into t into tau 2. So, this is the second equation that we have got. So, we have found out that if we can find out the shear stresses tau 1 and tau 2, we can relate them to the applied torque, and thereby we will get the torsional rigidity. Now, the next thing that we have to do is to apply the Bred's-Pathos theorem. So, which states that tau ds is going to be 2 GA into theta, where theta is the rate of angle of twist. Now, let us apply this for cell 1. If I apply this for cell 1, I get for cell 1 as tau 1 into pi r minus tau 3 into 2r is going to be 2g A1. A1 is pi r square by 2 into theta. So, let us go back and see how we have done that. So, what we have done for this particular cell, so we are moving around this cell. So, Q1 or tau 1. and q3 or tau 3. Now, if we move along the portion 1, we have tau 1 into the length which is 2 pi which is pi into the pi by pi into the total radius, half the circumferential length, half the total circumferential length, which is going to pi into the radius. So, which is pi into r, and then while we move here, tau 1 is in the opposite direction. So, we have to maintain one direction as we have discussed in the earlier lecture. So, if we are moving in cell 1, we are moving in clockwise direction, which is considered to be positive. Then therefore, we have positive tau 1 into half the circumferential length, which is pi into r. And then as we move through portion 3, it is in the shear stress is opposite to the clockwise direction. So, I have minus tau 3 into 2r, which is the length of the portion 3. So, that is what we have done. So, we have taken tau 1 into pi r minus tau 3 into 2 pi r, and that is going to give me the 2 into G A. A is A1, which is pi r square by 2 into theta. So, if I simplify this, this is going to be pi tau 1 minus 2 tau 3, and that is equal to G pi r into theta. So, this is another equation that we get in terms which relates tau 1 and tau 3 to the angle of twist theta. So, let me call this as equation 3. Now, let us move into cell. Now, if we move into cell 3, we again apply the Brett-Bethos theorem. Then we have to say that tau 2 into 2 pi r. 2 pi r is the entire length of the portion 2, and then plus, because we are moving in the clockwise direction, tau 3 into 2 r is going to be 2 g into half of 6 r square into theta. So, let us if I go and see, if I am moving with q2 or tau 2, then if I am moving in the portion 2, then I have tau 2 into 2 pi r, that is the total length of portion 2. Then when I am moving in portion 3, I am moving in the same direction, so the positive sign, and therefore, I have tau 3 into 2 r. So, that's how, and that's how I have got this equation. So, if I simplify this equation, I will have pi into tau 2 plus tau 3 is going to be 3 g r theta. So, this is the third equation that, or fourth equation, that relates the shear stresses to the angle of twist. Now, from equation 1, we have got the earlier one that we have derived. From equation 1, we have got that tau, from the previous equation that we got from the geometry of the deformed membrane, that 2 tau 1 was equal to tau 2 plus tau 3 tau 3. This was equation 1 that we had derived earlier. Now, we can say that from equation 1, 2 and 3, we can solve for tau 1, tau 1, tau 2 and tau 3 in terms of theta. So, we can solve for tau 1, tau 2, tau 3 in terms of theta. Now, once we solve tau 1, tau 2, tau 3 in terms of theta, this can be actually plugged in to equation, sorry, this is equation 3 and equation 4. So, this can be used in equation 2 and we can obtain the torsional moment in terms of angle of twist T, and which will give us the torsional rigidity of the cross section. So, now we will move on to a next problem which will help us to understand this concept further. So, this is another cross section that we have. This is also a thin walled cross section, closed cross section with two cells. So, let us name the cells as A1 and A2. So, let me draw the dimensions of this cross section. So, the dimensions of the cross sections are as follows. So, this length is 16 T. This cross section is also symmetric about the x axis. So, this is 16 T. So, this is a semicircle of radius 8 T. This portion is also a same semicircle with radius 8 T, and the entire cross section has an uniform thickness T. So, the thickness is uniform throughout the cross section and which is given as T. Now, if I draw the deformed shape of the membrane, I can draw this in this form. So, let me name this as H2, this as H1 and this as this as H3 and this as H1. Now, so one thing I should mention that I have arbitrarily chosen this shape of the membrane. H2 can be smaller than H1, does not matter, you will get the same result, but you have to stick to the shear flow according to the shape that you have chosen. If you choose H2 to be smaller than H1, so you should write the relation between the shear flow according to the deformed shape of the membrane that you have assumed. So, I have assumed this and I will stick to this deformed shape, and I will find out the relation between the shear flow Q1, Q2 and Q3 in terms of this deformed shape that I have chosen. So, this is the deformed shape of the membrane. So, let me call this as portion 2, this as portion 3 and this as portion 1. Now, from this membrane we can see that H2 is going to be H1 plus H3. Now, we have seen from our earlier discussion that H2 is basically shear flow, which is going to be Q1 plus Q3. So, this equation if I call this to be equation A, then this equation gives us the direction of the shear flow according to the deformed shape of the membrane that we have chosen. So, according to the shape of the membrane, the Q, if I choose this to be my Q1 in the clockwise direction, then my Q3 has to be this and Q2 has to be this. So, we can see that Q1 plus Q3 is going to be Q2 at this junction K. So, as we have discussed in the earlier section, so earlier lecture. Now, from this we get another additional information. Q2 can be written as tau 2 into T because we have uniform thickness T. This can be written as tau 1 into T and Q3 can be written as tau 3 into T. Now, from this expression we will get tau 2 equals to tau 1 plus tau 3. So, this is going to be our equation 1. So, this is going to be our equation 1. So, if the applied torque is mt, then mt can be written as 2a1 into h1 plus 2a2 into h2. So, let us find out what is a1. a1 is pi by 2 because it is semicircle into 8t is the radius to ht whole square, h1 is tau 1 into t, and then a2 is the area of the semicircle pi 2 into 8t square plus 16t into 8t, that in tau 2 h2 is tau 2 into t. So, this is the expression for mt. So, if I can find out tau 1 and tau 2 in terms of the Brad-Bethos theorem, in terms of the rate of twist from Brad-Bethos theorem, I can obtain the expression for mt in terms of theta. Now, using Brad-Bethos theorem, tau ds is equal to 2 GA theta. Now, for cell 1, we can say that tau 1 into pi into 8t minus tau 3 into 8t is going to be 2g, a is pi by 2 into 8t square into theta. Similarly, for cell 2, we can say that tau 2 into 2 into 16t plus pi into 8t plus tau 3 into 8, sorry, the radius is, diameter is 2. So, I will have a 2 here and a 2 here. No, sorry, this is the same thing. So, this is going to be 2 into g into area 2, which we have found out earlier. So, area 2 is pi by 2 into 64t square plus 16t into 8. So, this is going to be my equation 3, this is my equation 2, and this is going to be my equation 4. Now, from this 3 equation, I can solve for tau 1, tau 2 and tau 3 and can express theta mt in terms of theta. So, if you solve this, you will get tau 1 as 9.49 GT theta. Tau 2 is going to be 11.83 GT theta. Tau 3 is going to be 2.34 GT theta, and we will get MT in terms of theta as 1.033 into 10 to the power 4 into GT4. So, this is the answer that you can obtain by solving the equations that we have derived. Thank you.